we can work when we don't have enough steam coming from the other parts. And what we wanted was to find the optimal dimensions of these three elements of the plant. Okay? So our variables were these three dimensions. Dimension of the solar field. What we had was a file with expected direct solar radiation based on experience every hour of the year and the temperature. With this data, we can determine which is the steam mass that comes out from the solar field at every hour. And we had a maximum size. Then we had the tanks. We had to take into account that a tank cannot be arbitrarily large. So it can hold up to 8 hours capacity, but if we need more than that, then we have to build another one. The fixed costs of these were high. And then we had the auxiliary system, which had a legal limit, because at that time, the solar energy was subsidized in Spain. But of course, you cannot get subsidized if you produce everything with the auxiliary system that is using oil. So we had a legal limit of up to 15% of use of the auxiliary system. We cannot go beyond that, okay? And we had another variable, which was the load fraction limit. The load fraction is at what percentage of the full capacity we are working. So if we set a load fraction limit of 60%, it means that we'll never work under 60%. If we cannot reach 60%, we stop, okay? So, again, the model looked very simple, 4 variables, just simple bounds, but the problem was to simulate the operation strategy, because we had to do it this way. If there's enough steam mass coming from the solar field to produce at least at L, we work at L. If there's more than enough to